Okay, so welcome to the first hands-on session of the Basics to ASICs workshop. I hope that you enjoyed the amazing talks that we had throughout the day and found them beneficial. Okay, so in this hands-on session, we are going to use OpenLane to harden macros, and we are going to integrate a design of our own into the Caravel users wrapper and then harden the wrapper as well. So before we start, if you didn't already, please join the Slack channel, open source Silicon Workspace. There is a Slack channel there called Basics to ASICs workshop tutorial. This is the channel that we are going to discuss the material that we are going to go through throughout this session. If you have any problems with it, you can share it there as well. Concerning the prerequisites that was sent to you, I guess, yesterday at night or today in the morning, something like that, according to your timing. If you haven't already installed the prerequisites, if you haven't already set up your environment to be ready to go step by step, don't worry about that. The session will be recorded. You will be handed the sessions along with the slides. So you will have all the time in the world to go through the steps, and you will have the support from our team through the channel as well. So don't worry about that. Just focus on the session, try to grasp what we're doing, and that will be fine. Okay. So as I mentioned, the agenda for the day, we are going to start off by describing what is the design we are going to actually harden and integrate into the Caravel users wrapper, which is a simple design, serial parallel multiplier. We will start learning how to harden it using OpenLane, and then integrating this design into the Caravel's user wrapper and hardening the wrapper. So starting off with the serial parallel multiplier, you can check out this application note for full documentation about the serial parallel multiplier and the full details of how it's implemented in terms of gate level. But for the sake of our workshop, what you need to know is that our serial parallel multiplier basically takes two 32-bit numbers, performs the multiplication, and produce a 64-bit product. The multiplier has one parallel input, which is the X, where it takes all of the 32 bits parallelly, and one serial input, which is Y, and produces the product P serially. And that's where the name came from, serial parallel multiplier, as it has two inputs, one of them serial and one of them is parallel. The first module of our design is the SPM. The SPM basically is the one responsible for receiving the 32-bit input X parallelly and receiving with each clock cycle the least significant bit from the multiplier serially, and producing one bit at a time each clock cycle from the product P and sent as an output. Okay, so as you can see, this design is it's serial. It needs to be fed the least significant bit of the multiplier Y, and it produces the output bit by bit. So it needs we need to create a 4-parallel version of it, and that's our second module, which is mul32. So mul32 will be the one receiving the 32-bit multiplier and multiplicand X and Y. It will create a shift register for the multiplier, shifting it to the right with each clock cycle and feeding its least significant bit to the SPM. And it will also take the product P, shifts it to the product register, and to make the product ready after 64 clock cycles. And it also has a control unit which receives a start signal indicating that the multiplier and multiplicand are ready to be multiplied. And when the multiplication process is done, it sends a done signal as well as the final 64-bit product. Okay, so these are our two designs for the multiplier. You can find that the SPM modules is divided into 3 modules. The SPM and MUL32 we already discussed, and the final module is called user project MUL32. This is the one responsible for connecting the design to the Caravel management core. So it will be discussed later in the session. All the 3 design files, Verilog files, can be found as a pinned message on our Slack channel. So again, please, if you haven't still joined our Slack channel, do so. You will find in the pinned message a zip file called hands-on session 1 files, and it will contain the Verilog file of these 3 designs. Okay, so now that we got a quick introduction about our design, it's time to start hardening the macro using OpenLane. A quick recap on OpenLane. OpenLane is an automated RTL to GDS flow based on several components for design exploration and optimization. The flow performs full ASIC implementation steps from RTL all the way down to GDS, from running synthesis, floor planning, placement, clock tree synthesis, routing and optimization, and finally finishing off with the GDS file. All what OpenLane needs from you is actually 3 things. The RTL files, which is the design files that we just mentioned, a configuration file, and the PDK or the process design kit, which in our case we'll be using the Sky 130 PDK. Of course, as Dr. Shalan mentioned in his slide, this is a very abstract view of the open source ASIC design flow. It's much more complex than that. And even so, it can go beyond OpenLane to make sure that the flow ends successfully. But for the sake of this workshop, and for since this is the first time for many of you, you don't need to get into the details of the full flow. Now we start the OpenLane and Sky 130 PDK installations. This step was included in the workshop requirements document that was sent to you. So if you already done that, you don't need to do it again. Basically, all what you needed to do was cloning the OpenLane GitHub repo and navigating inside that folder that you just cloned and running make. The make file should pull the OpenLane Docker image and pulls and updates the PDK as well. You can check out the document that we sent you or the OpenLane GitHub repo to check the prerequisites needed before OpenLane installations from Docker to Python and other prerequisites as well. Once you make sure that you have all these dependencies installed on your machine, you can go ahead and run these 3 simple steps to install OpenLane. Okay, so once we have OpenLane installed, we start preparing the design data. In order to harden any design using OpenLane, you must have a folder for that design inside the designs folder. So we need to open a terminal window at the OpenLane folder and execute the following commands. Okay, so let's go ahead and do so. Let me open a new terminal window. Zoom in order to see it well. Okay, I have OpenLane installed under my desktop, so I will navigate to desktop OpenLane. Then it mentions that I need to get into the designs folder. we can go ahead and open the OpenLane folder to visualize what it actually contains. It installed some configurations and requirements, as well as the virtual environments. And you can find here that it installed the PDKs as well, containing the Sky 130 A and B PDKs. And it has a folder named Designs. This folder contains some template designs, which you can run the flow on them to start exploring more. And we need to create a new folder here with our design and add our RTL files as well. Okay, so we navigate to the designs folder. We then create a new directory called mul32. We navigate to that directory. mul32. And we create a new directory called source or SRC. And we should copy our source files, the spm.v and mul32.v to the source folder, and this should be the path to the folder that we need to copy these files to. Okay, so we can go ahead and copy. I have them under desktop. spm.v, and we will copy that to the current working directory. So we will use pwd, and inside the source file, since I'm inside the mul32, and we'll do the same thing for the mul32.v. We can go ahead and check the OpenLane folder designs. We will find that we created a new design folder called mul32. Inside it will be a source folder, and inside the source folder it should contain the two files or Verilog files of our design, the SPM and mul32. Okay, so what's next? Remember this demonstration of OpenLane, we mentioned that it needs the RTL files. We have that now. We need the PDK. It's already installed. So what's left is the configurations file, okay, the config.tcl file. In order to create a new configurations file, you have two options. Either you use an old configuration file and start editing, or create a new one, a new template from OpenLane. To do so, we need to pull the Docker image of OpenLane. So let's go ahead and do that. We need to navigate to the OpenLane directory. Okay. Now that we are inside the OpenLane directory, you should export the PDK root. Okay, please note here that the PDK root in default is the current working directory, which is inside the OpenLane folder /PDKs. And as we showed earlier, this is actually true. Inside the OpenLane folder, I have the PDKs. So you shouldn't worry about exporting the PDK root. You should actually worry about exporting the PDK root in case you have the PDKs saved in another directory. So then you go ahead and write export PDK root. But for the sake of the workshop, we are going to export the PDK root as well. PDK root, it's the current working directory inside the PDKs folder. Okay, now that we are inside the OpenLane folder and we are sure that the PDK root is correct, it's time to pull the OpenLane Docker image by running the following command: make mount. Okay, I guess I entered the wrong OpenLane folder. Sorry about that. Let's go ahead and export the PDK route and make mount. Okay, now that we have our Docker image mounted and the OpenLane container is on, we can go ahead and start running this command, which will create a template configuration file for our design. So first we call the flow.tcl file. We then pass the design name. Our design is called mul32. After that, we pass the flag, which calls that we need the initial design configurations. So we write initial design config. Okay, and then we will give the tag that we need to add two designs. We need to add the configurations file to the design folder, which is the mul32. So we'll go ahead and write that, add two designs. And then we will name the configuration file. So we'll pass it to config file, config.tcl. We will name the configuration file. So config file, and we will name the file config.tcl. Okay. This is the message you should expect, that there is a successful file, config.tcl file has been added to designs/mul32 with the default configurations. And it also mentioned that please update the values as you see fit. So I guess I can stay on this slide for a bit, as it's a long command. Again, this command is mainly to create a template configuration file and add it to the mul32 folder, which is our design directory. Okay. Now we can examine the generated configuration file using our editor. So let's go ahead and do so. Inside OpenLane, we navigate to designs, our newly created mul32 folder. We will find that there is a config.tcl file that has been generated. So we can go ahead and open that with our editor and see its components. Okay, so this is a very basic template. It just sets the design name. It mentions that the design name is mul32. It specifies the Verilog files path. It sets the path to the design directory /src/all the files. That's why we created the folder src, as this is the default Verilog files. It sets the clock port to clock CLK, and this is actually the naming convention that we use in our design. So we shouldn't change anything here. And it sets the clock period to 10. Also, this is the clock period we're working with, so you do not need to make any changes here. The thing that you need to change is that set a design score. Design score, this is a parameter indicating whether your design is a macro or a full chip. If your design is a full chip, you should set design score to 1. But since we are hardening a macro, so you should set design score to 0. And yes, that's it. That's the slide here. It changes. You should only change the design score to 0, and then you will have some text-specific configuration that you shouldn't change, and we go ahead and save our configurations. Again, to all the attendees, I know it's a little bit, it might be a little bit hard to follow step by step. We are doing our best to do so. But please, if you are stuck with any step for whatever reason, you can try and keep focusing with the session, and we can go back to this problem after the session on our Slack channel, and you will be sure that you will go on with the session material. So don't worry about that. Okay, so again, what we did until now is that we created a design directory called mul32 under the designs folder in OpenLane. We then created the source folder containing the our SPM and mul32 designs. We then needed to have a configuration file for our design. So what we did is we ran this command, which basically runs the flow mentioning that the design that we are talking about is mul32. It says that we need the initial design configuration, and please add that to the designs directory. And we mentioned that the configuration file will be named config.tcl file. And then we started to examine the configuration file. We did not change anything except that this parameter that the design is core. We mentioned that it sets the design name, where the Verilog files are, the clock port and clock period, and whether the design is core or not. It was set to 1, and we changed that to 0, again, because we are hardening a macro, not a full chip. And we mentioned that there are some text-specific configurations that are that you do not change. And for more about the OpenLane configurations, you should check out this README file. Let me go ahead and open that with you as well. This README file contains all the configurations that can be used in OpenLane and what exactly they stand for. So the configuration file is the most important thing while using OpenLane, since everything is automated. So the only thing the user can do is actually adjust these configurations, and it's up to the designer to take decisions about these configurations to find the best way to harden and optimize their designs. So again, this is a very important thing that you should always get back to while hardening your design. Okay, moving on. Now that we have our configurations set, we have our RTL. Now that we have our RTL files in place, we have the PDK set, and now we have our configuration.tcl file set. We are ready to run the OpenLane flow. How to do that? All you need to do is to call the flow.tcl command and pass on the parameter of the design name mul32. And here it's optional to pass a tag which labels your run. We will call it here run1. If you did not pass that tag, the run will automatically be named after the timestamp. This tag specifies the folder where all the OpenLane output of logs and reports will go through. In other words, the run path. And this tag specifies the folder name or the run name. It's always a good practice to name your tags in order not to get confused with different runs. Okay, so we are still in the OpenLane container. We will go ahead and run flow.tickle. We will pass on the design name, mal32. Then we will pass the tag run_1. Okay, this should start the OpenLane flow. You will find that it names each step. So yes, is there any question? In the back, okay. It will run the steps from synthesis all the way up to producing the GDS files. While it's running, I think I can stop here to make sure that people are trying to catch up. Okay, so again, for people who are trying to catch up, let's recap while the flow is running. After cloning OpenLane and running make, we created a new folder inside the designs folder under the OpenLane directory named mal32. We then created another folder inside that called SRC, or source. We copied the source files, the SPM and mal32 to the source folder under this directory. After that, we needed to create a config.tickle file. So we navigated to the OpenLane folder. We exported the PDK root, and we mentioned that the PDK root is the root where the PDKs reside. By default, they are under the OpenLane directory /PDKs. And you should export the PDK root if you have them stored elsewhere. Then we ran make mount, which basically fetches the Docker container. And we ran the following command to generate a template configuration file. We just run the flow.tickle file. We pass on the design name. We pass that we need the initial design configuration, and we wish to add it to the designs folder. And we named the config file config.tickle, and this created a configuration file under OpenLane designs /mal32. We then examined the configurations file, and we changed design score to 0, as we mentioned, because we are going to harden a macro, which is going to be a part of a chip, not the whole chip. That's why it's not core. Design score is set to 0. And we left everything else. We did not change anything. And we mentioned that you should always get back to this README file, as it has all the documentation you need about the OpenLane configurations. And we are now running the OpenLane flow. So let's take a look about that. You'll always find that step 24 or whatever the step number is, but most probably it's going to be step 24. Sometimes these things change after an update or so. But detailed routing is always the one that's taking most of the flow time. And but I guess it won't take that long. It'll take around maybe an extra 2 minutes or something. Okay. Can I have, by the show of hands, how many of you are actually running the flow right now? Okay. Okay. Again, for those of you who are not able to follow step by step now, don't panic. You will have the slides and the recorded session, and you will be able to do that at your own timing after that. So don't worry. Yes, the warning we got, it will be explained in details in a while. Step 27 seems to take the longest time. We will take a look at that as well. Okay, so hopefully after it finishes, I guess it will take maybe, yeah, okay. So this was the longest step. Now it should take an extra 1 or 2 minutes. At the end of the flow, to make sure that the flow is successful, you should find the following message, is that there are no hold violations in the design at the typical corner, and there are no setup violations in the design at the typical corner, and success flow is complete. So this is the green message we all hope to see on our console after we finish. Okay, we can go on, since someone mentioned that there was a warning at the beginning. It's very important to take care of the flow logs, even if the flow was successful. As you are going to see, our flow will run successfully. However, it produced a warning message that the current core area is too small for a power grid, and the power grid will be minimized. What does that mean? It actually means that your core area is too small for the power grid. Who defined the core area? Let's go back to the configurations file. We did not mention anything about the core area here, right? So the core area was left to be set by default. How will it be set by default? The default core utilization is set by OpenLane to 50%, and the default aspect ratio is set to 1. This means that the core area will be a square, since the aspect ratio is 1, so the length will be equal to the height, and the core area will actually be double the size of the total cells area. Since the core utilization is 50%, so we will take all the cells area, double that in order to have the utilization of 50%, and this will be your core area. So this is how the core area is actually defined. طيب, يعني what did we mention anything about a power grid in the configuration file? That is a no as well. We did not mention anything about the power grid. So the power grid by default have here you can find this parameter called floor planning PDN, power distribution network vertical pitch, is set by default to 153.6, and the horizontal pitch is set to 153.18. This means that the step or pitch between every power strap is 153.6, and this is too high or too big for the small core area that we defined. That is why the power grid will be minimized. So the default power distribution network vertical pitch and horizontal pitch will be reduced automatically by OpenLane from around 153 to around 32. Okay, so I guess we finished here. As you can see here, success flow is complete, but we have the following warning. okay, which we are discussing now, that the current core area is too small for a power grid, and the power grid has been minimized. This tells us a very important lesson that if the flow was successful, please take a look at the logs carefully, make sure that everything went fine. Here, OpenLane did an automatic solution, but what if you as a designer find that the pitch is too small to be 32, for example? Then you must take a careful look at the warnings, make sure that you understand them and understand what they did. There is another warning here that there are max fan-out violations in the design of the typical corner. This warning is actually okay to continue with. It doesn't make any significant changes to the design, not like the other warning that we discussed. So this means that even if the flow is successful and you see this green output line, make sure that you take a careful look on your warnings, because not all warnings will stop the flow. Actually, as we saw here, we have 2 warnings and the flow was successful. Now let us take a look at the OpenLane outputs. So as the flow runs, it produces lots of files such as reports and log files under the run path. Let us check the run path. Okay, so here I am in the OpenLane directory. I get into the designs folder, our design mul32. You will find that a new folder has been created called runs. You can open up this folder. You'll find run1, which we defined as the name of our run in the tag. And you will see that we have another configuration file. By the way, this configuration file is the full configuration file of your design. Every parameter that you don't set in this configuration file, it will be set as the default OpenLane parameter in the configuration file. In this configuration file. Okay, so it also produces reports for every step: clock tree synthesis, floor plan, placement, and it produces the results, which is the def file or the layout of your design after each step in the results folder. As well as other outputs as well. Okay, so where is all of that? All of that is under the run path. The run path you will find under the design name, runs, the name of your run, and you will find all the outputs. So what are the outputs we are interested to take a look into? The first file is the runtime.yaml file. OpenLane records the runtime of different steps into this file. So let's take a look at the runtime.yaml. Okay, let me stand and zoom in a little bit. This file basically tells you information about how long did each step take. So if we go to the end of the file, you'll find that the flow was completed after 8 minutes and 11 seconds. And it was routed after 5 minutes, 50 seconds. What I mentioned that if we search here for detailed routing, you will find that the detailed routing took around 3 minutes, 52 seconds, which is basically half the time of the whole flow. Why is this useful? Because you can find where did the delay come from if your design took too long to harden, and be sure that if it took more than normal, that maybe you have something there that you should go check the logs of that specific step. Okay, so what else are the outputs that we should be looking at? We can, of course, check the final GDSII. Remember, this is the purpose of running OpenLane. It's changing the RTL files to the final GDS file. So where can I find this GDS file? You can find it under your run path, results, final GDS. We will go in that together. So the run path, again, under runs, the name of your run. Then we will go to results, final GDS, and you will find your mul32.gds file. I think it was included that you should have installed Klayout, or you should install Klayout in order to be able to view the final layout. So let's go ahead and open that. So this is our final layout. This is our hardened macro. And this is the final GDS file of our design mul32. Okay, of course, we will not go through the details of analyzing the GDS file, but you can do that if it's if you are checking your own design after that. What other OpenLane outputs should we look at? There's a very nice feature in OpenLane, I guess I mentioned it between the lines, is that you can examine the layout after each step. So you can examine the layout of your design after planning or placement or clock tree synthesis, etc. So let's take an example that I wish to view my layout after placement. So what should I do if I want to view the layout after placement? First, let's go to results. So I am under the run path, results, and I want to see my design after placement. I go ahead and enter to placement. I find mul32.def file. So I have a def file, but I am missing the left file for it. Okay, so of course, after placement, you still haven't reached the final step to have a GDS file, .gds file. So you only have a def file, which needs a left file in order to be viewed by Klayout. From where can I get this left file? You will find under the run path temp folder. You will find the left files there, which you can use with each step. Okay, so let's take that step by step. I am under the run path, run one. I enter the temp folder, and I will find that I have 3 left files. One called max, and the other min, and the other nominal. Okay, so you can take the nominal left file. We will take a copy of that. Okay, so I will go ahead and take a copy of that. I will go ahead under results, placement, and paste it there. If any of you are thinking, why are we actually copying the left file? Why don't we just mention on Klayout that the left file is in the X directory, for example? The thing is that Klayout, in order to view a def left design, both files should be in the same directory. That is why we took the left file and we pasted it to be inside the same directory as the def file. Okay, so we will go ahead and Klayout. Klayout is here. We will go ahead and write file, import. You will find here a def left option. We will then go ahead. We will go ahead and find our directory here under designs, mul32 runs, run one. This is your run path. And we said that we wish to view the result of placement. So we go ahead to results. placement, and we will choose the def file, mal32.def. We will open that. Automatically, it attaches the left file inside the folder. If it doesn't do that, make sure to add your left file here using this add sign, and we will import a new layout in a new panel, and we will press OK. And here is your design after placement. So again, why is this feature so important? Is because your flow might fail at a certain step. For example, your flow might go through synthesis and then floor planning, and then it will fail. So you can go ahead and check the def file generated in that step or the step before in order to start debugging and checking what actually went wrong while generating the layout. Okay, so this is a very important feature as well provided by OpenLane. And we continue on examining the OpenLane. This is the layout comparison, of course, the layout after placement and the layout of the final GDS file. We will then continue examining the OpenLane outputs. What else does OpenLane outputs and what other features does OpenLane give the user? OpenLane ASIC flow ends with physical verification. This means that it begins by streaming out the GDS file, following by running design rule check, layout versus schematic, and antenna checks if the antenna checks are enabled on the design. So it produces at the end automatically two very important reports. The first is a final summary report, which is produced under this path, our run path, /reports/metrics.csv. We will open it and discuss it. But for now, let's mention that this report contains information about the Hardening design, such as the total number of physical cells, some information about the power consumption, the core area, number of violations, and other metrics as well. So let's go ahead and find this report. Again, this is the run path. I'm inside my run path. I'll go ahead to reports and I will find metrics.csv. Let's open up this file. Zoom in a little bit. Okay, it mentions the design path, the design name, the name of the run, the total run time, the die area. Of course, it mentions a lot of things here, such as the number of violations, the while lengths, the total number of vias. What else? It mentions here in details the cells used and the total number of physical cells. It also mentions the core area. Here it will start mentioning some metrics about the power consumption, the power leakage, and other stuff. Okay, and here it mentions the thing that we talked about in a prior slide, which is the core utilization. It's set by default to 50%, as I mentioned, and the aspect ratio was set to 1. And remember, we talked about the PDN vertical pitch and horizontal pitch, and we mentioned that OpenLane automatically reduced them. So you can find these values in this summary report as well. And yes, so this is one of the very important OpenLane outputs, which is the metrics.csv, which acts like a summary of your final design. The second report we wish to talk about is a final manufacturability report. It's also produced by default. This manufacturability report goes under the run path /reports/manufacturability report. So actually under the same directory as the final summary report. What will this report contain? It will contain the magic DRC, the layout versus schematic. DRC stands for design rule check, and the antenna violations summary. So we can go ahead and check out this report. Just a second. Okay. So yeah, this report mentions the design name and the running directory, and then the DRC summary that we have total DRC violations is 0. The total errors for the layout versus schematic is 0. We didn't run the antenna summary, that's why there is no report found. But you can go ahead and check the configuration file in order to run the antenna violation checks. And yes, this is I think this is it for OpenLane. I think we can take a quick 5-minute break or something, and then we will come back discussing how to integrate our design into the Caravel's user wrapper and how to harden the wrapper after that. So let's take a break for 5 minutes. Okay, so now what we have done in this session so far is that we learned how to install OpenLane, how to add a design to the designs of OpenLane to be hardened, and what are the steps you need to do to create a configuration file and run the OpenLane flow, as well as examining the OpenLane outputs and how what are the important outputs which you need to take close care to after hardening the flow ends. Okay, now we will go to the second part of the session, which is integrating the design into the Caravel user project, user wrapper. And first, let us recap what is Caravel. Of course, Caravel has been better explained by the speakers before me. But just as a quick recap, we can mention that Caravel is a template chip for the Open MPW and Chip Ignite shuttles. It provides the needed infrastructure for these Open MPW chip and Chip Ignite designs. And in addition to the, of course, this infrastructure is the pad frames, pad frame and means for clocking and resetting. And in addition to the pad frame, it contains 2 main areas, the management area and the user's project area. The user's project area is around 10 millimeter squared, and the whole chip is around 17 millimeter squared. So the user's project area is actually 2/3 of the whole chip. And this is another view of the Caravel architecture. The area highlighted in red is the management area, and the area highlighted in blue is the user project wrapper or user project area. And at the beginning, I guess you do not have to overwhelm yourself with each single detail of the Caravel architecture. But if you wish to learn more about the Caravel architecture, the link below is their GitHub repo in the area where they discuss the Caravel architecture in details. But let's focus on the user's area, since this is the area where our project will reside in. So let's see more information about this area. The user's area is also called the user project wrapper. As I mentioned, it's 10 millimeter squared of silicon area. It has access to 4 supply domains and 38 IO pads. These IO pads can be configured through the firmware on the management SoC. And it also has access to 128 logic probes, as well as access to the management SoC wishbone bus. And if we want to talk about the users project area integration, it's made the Caravel layout is pre-designed, and all you need to do as a designer is provide a user project wrapper GDS, and it will in the tape-out process this user project wrapper will get into the vanilla Caravel to be ready for manufacturing. So as a user, all what you need to do is provide a valid user project wrapper GDS file, a valid hardened user project wrapper, and the else has been basically done for you. But of course, this project wrapper, there are some project wrapper requirements to ensure that this process will be successful. Is that your wrapper must have the area that was mentioned before, which is around 10 millimeter squared area. The top module should have the fixed name of user project wrapper. You should not change the pin placement or pin sizes or core rings width and offset. Also, you cannot change the PDN vertical and horizontal straps width. And again, you shouldn't worry about that, since we are going to already to use a ready-made user project wrapper. So even this step has been done for you, but you should take a note of these requirements and make sure that you do not change any of these during your design. Okay, so now we will talk about integrating the serial parallel multiplier into the user's wrapper. We have our design, and we understood now what is the user project wrapper. We need to integrate our design into this wrapper. So the SPM is going to be implemented in the user's project area. As you can find here, this is the user project wrapper block diagram. Here are the IO pads and the logical analyzer and the IRQ and the wishbone bus. And the management core will communicate with the SPM using the wishbone bus. Of course, there are other means of communication, such as the logical analyzer signals. But for the sake of this workshop, we we have done the communication between the our SPM and the management core using the wishbone bus, and the wishbone communication will be explained thoroughly in this workshop. So here comes the use of our third and final module, which is called the user project MUL32 module. This module is the one responsible for communicating with the Caravel's management core through the wishbone bus. So basically, this module contains a wishbone interface, which can be used to write into the multiplier and multiplicand registers, as well as feeding the wishbone interface the output of the multiplication, which is P. It will also get the start signal and send the done signal to the wishbone. The start signal will not be sent unless the multiplier and multiplicand are both successfully written into their registers, and the done signal will not be sent unless the multiplication process is done. So this is what concerns our final module, user project MUL32 module, which is also you should have downloaded already in the beginning of the slides. And now let's talk about the wishbone communication in a little bit more depth. First thing you need to know is that the wishbone communication, as we mentioned, wishbone bus, as we mentioned, is used for communication between the management core and the peripheral implemented in the user's project area. The peripheral is also called a slave, and the management core area, the management core here is called the master. And why is that? It's because the management core will be the one initiating any read or write operations. You should also note that the wishbone bus is a shared bus among all peripherals in the user's project area, which means that at any point of time, the management core can only communicate with one slave or one peripheral in the user's project area. So how can this communication be done? How can the wishbone start communicating with the peripherals? or slave ports. There are 10 signals used to read and write to a wishbone slave. These 10 signals start with the two trivial signals, the clock and reset. Of course, we all know, I guess we all know what the clock and reset actually does. But the reset mainly, if you have multiple peripherals or slave ports, the setting reset to 1 will restore the status of all the registers to 0. Moving on to the signals, we have the strobe and bus cycle signals. Think of these two signals as the enabler of any slave port. So if these two signals are high, it means that there is a valid data transfer taking place, being read or write. In either case, both these signals must be set to 1. Sorry for that. Then we go to the signal called write enable for input. The write enable signal is also a 1-bit, so it can be 1 or 0. If it's 1, it means that we have a write operation. If it is 0, it means that we have a read operation. Then we have 4 bits for select, called select for input. When you are writing to a register, it's a 32-bit register. Let's say I want to write to the first, only the first 8 bits of that register. So then this select will have 1 and 3 zeros, meaning that I only want to write for the most significant 8 bits of the 32-bit registers and leave the others the same. So this is the select for input. Then we have the 32 bits of input data. This is, of course, the data that is written from the master to a slave in a write operation. After that, we have the 32 bits for the input address. Each slave port or each peripheral is mapped to an address in memory. WBS address specifies that address. So before any read or write operation, you must check the address sent by this signal in order to read and write from that specific register. These were the input signals. We have 2 output signals. The _O stands for output and _I stands for input signals. So we have 2 output signals, one of them being the acknowledgement and the other being the output data. The acknowledgement is a single bit signal that is set to high after a successful read or write operation. So this signal shouldn't be set to high except after we are sure that a successful write operation has been done to a register or a successful read operation has been done from a register. So in our case, for example, we have a serial parallel multiplier. Let's say I want to make, I want to read from the product register. The acknowledgement will not be set to 1 except after the multiplication process is done, because before that, the product will not be ready to be read. So the acknowledgement signal will be delayed until the multiplication process is done. Then it will be set to 1 and the product will be successfully outputted in the output data. Okay, so the acknowledgement is a very important signal and it is set to 1 only after a successful read or write operation. The final the final signal is the output data. It's also 32 bits. And of course, this is at the end of a read operation. The data sent on this signal is the data stored in the slave port or register with the address specified in the input address. Okay, now that we understood the signals, let's take a look at the wishbone read and write operations wave 4. In a typical read operation, as we mentioned, we must have the strobe and cycle both high, because without them, there is not a valid data transfer taking place. So we have the strobe and cycle set to high. The write enable will be set to 0. since this is a read operation, not a write operation. So it, as you can see, it's 0. Data in does not contain anything because this is not a write operation. We do not need the data in anything. The address specifies the address. Let's say that this is the address of the P register or the product register that I want to read from. So I specify the address in this signal. And it takes, here it takes 1 clock cycle for the acknowledgement to be set to 1 and the values inside the P register to be outputted in the data out signal. Please note here that, as I mentioned, if the multiplication process was not done after 1 clock cycle, let's say it took 2 clock cycles, this acknowledgement signal will stay low and will only rise after 2 clock cycles after the multiplication is done, and the values of the P register will be outputted then. Okay, so the write operation, mainly the same things. In order for a valid data transfer to take place, we need to have the strobe and cycle set to 1. So here both of them are high. This time we have a write operation, so the write enable should be set to high as well. Here we have data in. Let's say that we want to write this X to the multiplier register, for example. So we specify the data in to be X. We specify the address. This address should be pointing to the multiplier or multiplicand address, whatever the register we want to write into. And then after 1 clock cycle, the acknowledgement signal will be set to high, acknowledging that the successful write operation has taken place. Now that we understood how the communication occurs, how do we read and write from a register, it's time to mention how many registers do we actually have in our design. So we mentioned that our design has 2 registers. Sorry about that. Has 2 registers, MP and MC, standing for the multiplier and multiplicand. Each of these registers are 32 bits. So that's 2 registers or peripherals or slave ports, whatever the naming is, but that's 2 of them. Do we have any other registers? Yes, we have a register for the product, but the wishbone bus width is only 32 bits. So since our product is 64 bits, it will be divided into 2 registers. So finally, we will have 4 registers. Okay, their names in Verilog are MC, MP, P0 from the least significant 32 bits from the product, and the most significant 32 bits from the product. And here are the addresses, their addresses in memory, and the naming convention of the register we used. Note that these registers are memory mapped, which means that they can be accessed using their address in memory. So yeah, these are the 4 registers that are used in our design, or slave ports that are used in our design. So to conclude this part of the session, this is the look at the slave port block diagram. We can find that a slave port for the multiplier, for example, the slave port called MP, will have a connection to the wishbone clock and reset signals. It will have the ANDing of the cycle and strobe signals as the enabler of this port. And it will have data being fed to and be connected to the WBS data out as well. The difference between the slave port of the multiplier and the product, for example, will be the acknowledgement signal. For the multiplier or the multiplicand, we will only need to write to these registers. We will not need to read from them. That's why the acknowledgement signal will be set to 1 if a valid data transfer is taking place. as well as having the write enable set to 1 because it's a write operation, and the address will be set to the address of the MP register. Okay, so these are the 3 conditions that needs to be set for the acknowledgement to be set to 1 in this slave port. If we look at the slave port for the for one of the product registers, we find that the difference here is that the write enable is the not of it because it will be set to 1 after a read operation, not a write operation. Of course, it will the address should point to the P0 register, not the MP register. And we have a done signal added to the AND. This done signal, as we mentioned, is the signal set to 1 after the multiplication process is done. This means that you cannot acknowledge that a successful read operation has been done from this slave port unless we are sure that the multiplication is done. And this done signal is, of course, related only to our design of the serial parallel multiplier. Okay, so I guess now we took a better look and started to imagine how the communication goes between our design, which is the serial parallel multiplier, and the Caravel user project. And now it's time to harden the user's wrapper, or since we have the Verilog files ready and everything is in place with the user proj mul32 Verilog file, it's time to harden the user's wrapper and have our design, our wrapper ready for fabrication. In order to harden our design, we will use the Caravel user project example. This is an example that was made to ease the hardening process. It's a user's project example provided, which can be used as a starting point for our project. Okay, this example is basically a simple 32-bit counter, which has connections to the wishbone port, the logical analyzer probes, and the IO ports. You can check out the documentation of this example under their GitHub repo, but we are going to use this Caravel user project example as a template to start our project. Okay, that brings us to setting up the environment. Setting up the environment was part of the workshop requirements, the document that was sent. So again, if you didn't have the time or didn't get to setting your environment successfully, don't worry about it. You will have the time you need and you'll have the support you need to set it up successfully. So to set up your environment, you need to create a new repo based on the Caravel user project template and make sure that your repo is public and includes a README file. So there is a simple way to do that. It's just to click on the following link. This will create a new repository from Caravel user project. And of course, you need to be signed into to GitHub in order to get this page. Let's call the repository user proj mul32. Okay, I already have that repo because I already set up my environment, but that's what you should do. You should write the repository name. Let's have it all user proj mul32 and make sure that the repo is public, and the repo will already have a README file because it's cloned from the Caravel user project, so you don't need to worry about that. And then you will create the repository from template. Okay, so this is the step I already did. After I create my repository, I go ahead in my work space and open up terminal and write the following command: git clone your GitHub repo. If you did not set up your environment, please try not doing that now. Because setting up the environment might take some time. and it will take your concentration away from the session. So if you didn't set up the environment, you can start setting it up after the session ends. Okay. After that, sorry. After that, after I cloned my repo, I should navigate to the project name. Okay. Let me show you here. This is the folder you should get after cloning your repo, right? User project 32. If we go ahead and open that folder, we will find that it contains multiple files of def, docs, GDS, left files, and others. You should not find these folders yet, okay? These folders are because I already set up my environment and made and hardened the design before. So you should not find, starting from dependencies, you should not find these folders yet, okay? So you will get your user project 32 folder without these directories. Okay, so to continue setting up our local environment, we need to open up terminal, create folder called dependencies. I went ahead and did that, but let me show you how that was done. Okay, so I go ahead and navigate to the user project 32 folder. Now that I'm here, I need to create a new folder named dependencies. I already created that folder, so I will not do it again, but you should go ahead and create a new folder called dependencies. Then you should export two routes, a route to OpenLane called OpenLane route. This will contain the OpenLane source files as well as the PDK route. So our recommendation is to export the OpenLane route and the PDK route under the same dependencies folder, and that's why we created the folder dependencies. And a very important note here is that exporting the OpenLane route and PDK route should be done every time you start a new shell. So these two commands are not only for the first time you're setting up your local environment. If you close the terminal and open a new shell to continue working on your project, you must export these two routes every time you do that. Okay, so since I've opened up my terminal for the first time, so I have to export my OpenLane _ route, and that will be inside my current working directory under the dependencies folder, under the folder I named OpenLane _ source. Okay. Then I should go ahead and do the same thing for the PDK route. So the folder was named PDKs, and this is the PDK route. Okay, so as I mentioned, these two commands shouldn't only be while setting up your environment, it should be run every time you open up a new shell and start working on your project. Okay, we also, in setting up your environment, we recommend exporting the PDK you wish to use. So here we use the Sky 130B PDK. You should export the PDK variant depending on the shuttle you wish to submit your project on. If you don't know exactly what the shuttle requirement is, you can leave it to the default. Most probably it will have the most recent PDK as the default value. So if you don't know, you can just skip this part, and then you should run make setup. Okay, so I should go here and run make setup. Of course, I already did that part, so I won't run it again. But this make setup will set up your environment by installing a Caravel Lite, which is a light version of Caravel. We install Caravel Lite because Caravel would be too heavy for the project. It will take a lot of memory, and you don't need that. So Caravel Lite will be the one installed. It will install the management core for simulation. It will install OpenLane to harden your design, and it will install your PDK. So let's go ahead and see how these files are installed. So here I am in the project directory. You will find after you run make setup, you should have these three folders, okay? The first one being dependencies, the one you created will have the OpenLane source and the PDKs. Inside the PDKs, you will have the PDKs installed, and inside the OpenLane source, you will find the source for OpenLane to be able to harden your designs. Not only that, you will also find a new folder here named Caravel, which contains the Caravel Lite version, and you will have the management core wrapper folder, which contains the management core for simulation. So after make setup, make sure that you have these four directories installed. Let me say that again. The four directories installed: Caravel, management core wrapper, and under dependencies, you should have the OpenLane source and the PDKs. Okay. Once you reach this, please remember that the SPEF, SDC, and SDF folders, you shouldn't have them until now. You should not have them until now. These are directories that are produced after hardening. Just because I hardened before the session, these folders are produced. You shouldn't have them, so you shouldn't worry about that. Once you have these four dependencies installed, your environment is ready. So setting up the environment is done, and you are now ready to start hardening your wrapper. Before we start talking about the steps of hardening the wrapper, let's talk about the hardening techniques. Now we are not hardening a single macro as we did in the first part of the session. We are hardening a project wrapper. So while hardening this project wrapper, there are three available options. The first option is to harden your design first, and then insert the hardened design into the project wrapper as a black box, and then harden the wrapper. Okay, so we are going to harden our design, take the hardened macro, place it into the project wrapper, and harden the project wrapper as a whole. So this is the first option. The second option is to flatten your design with the wrapper. So just have your design flattened and go ahead and harden your project wrapper all at once. Okay, no hardened macros. The third and final option is basically a mix of both, where you can use multiple macros, multiple hardened macros, along with some design hardened with the project wrapper. So in our case, in this workshop, we are going to go with the first option, which is hardening the design first, and then inserting the design into the wrapper, and then hardening the wrapper. So with that option, the first thing we need to do is to start hardening our design. To harden the design, we first need to add the SPM source files, which are the three files, but this time not only mal32, we need the user project mal32 file. So we need to copy these source files into the directory under the project name, Verilog RTL directory. So let's go ahead and do that. I think we can minimize this a little bit. Okay. So here I am in my project directory. I go ahead under Verilog RTL, and you will find the project wrapper Verilog file and the project example Verilog file. The project example is the one that's set by default, which is the counter. So you need to add your own design in this directory under Verilog RTL. Okay, so let's go ahead and copy these 3 files, paste them here, and now our design is in the correct place. Next, we need to navigate to the OpenLane folder under our project directory and make a copy of the user project example and name it with our name, which is user project mal32. So let's go ahead and do that. I am under the project main directory. There is a folder there called OpenLane, and please note this OpenLane folder is different from the OpenLane source under the dependencies. What we are targeting here is the OpenLane folder directly under the user project mal32. Go ahead and open OpenLane. You will not have that folder. Okay, what you should do is duplicate the user proj example folder, rename it to user proj mal32. Okay, I already did that part, so I can throw that to trash. So again, what we did here is that we duplicated the user project example folder and named it with our new project name, which is user proj mal32. After that, since we are talking about hardening using OpenLane, you should always remember to check the configuration file before going ahead and start hardening your design. So we need to edit the configuration file under the directory that we just created. So let's check the directory we just created. You will not find the runs folder. Again, this is because I already did the steps, but you will find these 2 files, a configuration file and the pin order configuration file. Let's go ahead and open this config.tcl file. Okay. What should we do to this configuration file? It mentions that we should change the design name. The first thing we need to change the design name. If we go ahead to the config.tcl file, you will find that the design name was set to user project example. You should change that to user project mal32 to the new project name. What else? We should specify the design files. So under the set Verilog files, you should include all the 3 Verilog files. So let's go ahead and do that. Here, it was just defining the user project example file. So we change that to user project mal32. And then we add this backslash. You can go ahead and take that copy, paste it here. We have another 3rd file, so paste 3 times and change the names. Our 3 modules are user project mal32. Then we have mal32.v, and the final one is spm.v. Okay, so right now what we did is that we changed the name and we specified the design files path. You should also remove the clock net because it was set to the counter clock. This is something related to the old design. You do not need to define a clock net in our case. So we'll just go ahead and delete that line. Okay. And you should increase the target density to 0.35. So we can see here that we have a variable called target density. We will go ahead and change that from 0.05 to 0.35. Please note that this change is not something you do with any design. It's not something by the book that whenever you start up a new project, you go ahead and change the target density to 0.35. As I mentioned before, the configurations of OpenLane is up to the designer, and he or she must take decisions concerning how the final design would look like, related to optimization and power consumption and other factors as well. So since we already hardened this design, we are telling you that the target density being 0.35 will be okay for this design. It might not be okay for other designs, and this decision should be based on the
Zeyad, can I say something here? Let me interrupt you and say something here. Okay, so the PL target density stands for placement target density, which eventually specifies how close the cells will be placed relative to each other. So 0.35 means that if we take like a small area and then we measure basically the number of placed cells within this area, we'll find that these cells occupy 35% of that area. Okay, so basically the rule of thumb while using OpenLane is to set this value about 5% above the core utilization. So eventually here in this particular macro, we are setting the core utilization, or basically we didn't set the core utilization, and actually we are not going to rely on the core utilization that was basically is the default value from OpenLane. And why is that? Because we are specifying the actual floor plan. So we're using the absolute mode, and then we give the actual dimensions. So this 0.35 has to do with the core utilization, which is not set, and we cannot set because we're using the absolute floor planning mode. So eventually, Zeyad ran the flow one time, okay, with any value for the target density because he doesn't know anything about the core utilization, and then he examined the reports and the logs coming out from OpenLane, and then to identify basically what's the core utilization for this particular absolute floor plan. And then the core utilization was 30%, so he added to that 5%, which makes the target density 0.35. Okay, go ahead, Zeyad.
Okay, thank you, Doctor. So yeah, since the doctor mentioned the last detail that we were going to talk about, which is the absolute using floor planning sizing to setting floor planning sizing to absolute and setting the die area dimensions. These were the changes that needed to be done to the config.tcl file. So we can go ahead and save that config.tcl file and close it. And now your design is ready to be hardened. So inside the main projects folder, all you need to do is run this command, which is make and the project's name. This command will run the OpenLane's ASIC flow and generate the final GDS file of our design. So let's go ahead and try and do that. So we'll go ahead and run make user project mal32. and it will start the OpenLane flow. A quick note here, if the logs are different, if you find that the OpenLane flow logs are different, this means that most probably you are on the older version, so you can go ahead and recreate recreate your repository, or you can update the Caravel Git branch. But anyway, both of them will lead to the same results. So either you have this interface or the other one which displays all the OpenLane logs, it will have the same result at the end. This is the OpenLane flow that we did, so we will not wait for it to finish. So I can go ahead and quit that, because I already have one run here being named done, and this is the final OpenLane flow, because this OpenLane flow took around 20 minutes to harden, so we cannot stay all of that in the session. But what you need to note is that once you run the OpenLane flow using this command, make user proj mul32, it will create a runs folder, and this runs folder will create a run name with the timestamp, and you can find your OpenLane outputs, which we discussed in the first part of the session, in this folder as well. So if we go ahead and see my finished OpenLane output, you can find here the runtime.yaml, which specifies that it took 19 minutes to harden. That's why I terminated the one before. And you will find the reports and results and everything. What we can take a look at is the final GDS file. So again, you will find it under results, final GDS, user proj mul32.gds. You can use klayout to view that. And this is our design. This is our hardened user project multiplier. Of course, you can find that the dimensions are a little bit bigger than the one that we did in the first part of the session, and that's because, as the doctor mentioned, we specified the die area width and height, and of course it used a bigger width and bigger height, and took this rectangular shape, not the square shape that we saw earlier in the session. And if you make the flow run till the end, you will not find the warning message that we talked about, that it will reduce the PDN, because it will not need to do that, because the core area will be more than enough. Okay, so right now that we hardened our design, it's time to harden the wrapper. As we mentioned, the plan is we are going to harden our design. We will use this hardened design as a black box or as a macro inside the user project wrapper, and then we will harden the wrapper. So now that we need to harden the wrapper, we first need to make a little changes, some little changes. The first one being going to project name Verilog RTL and added the file user project wrapper.v to change the name of the module being instantiated from there, from user project example to user proj mul32. So let's see what that means. We go back to the top directory of our project. We go ahead under Verilog RTL. Let's open up the user project wrapper.v. Okay, first it defines the module itself, the user project wrapper, and then here is the it instantiates user project example. So we will change that to user project mul32, And keep in mind that the macro here, or the instantiation is called MPRJ, standing for mega project. So this is the only change you need to make. So we will save the file. Of course, you can, after the session, you can take a look at these Verilog files in details. And if you have any questions, you can ask us. But just for the sake of the time, we cannot go into details of these Verilog files in this session. So this is the first change we needed to make, which is changing the module being instantiated from example to multiplier. And then we need to make some changes to the configuration files of the wrapper as well. We are now going to harden the wrapper. Hence, we need to go to the configuration files and start making our adjustments. So let's go ahead and find this configuration file before we see what we need to change. Under the top module, the top directory of the project, you go ahead under OpenLane, user project wrapper, and you will find this config.tcl file. Again, you shouldn't find this run folder yet, but I already done the hardening part. Let's go ahead and open this configuration file. Let me zoom in. Okay, let's first take a look at the changes we need to make. The first thing you need to change is to change the black box Verilog and views to the to user project method 2. You will find here the common black box Verilog and views. We mentioned that we are going to deal with the user project multiplier as a black box or a macro inside the project wrapper. So we need to specify the path to the to its Verilog file and to its left file and to its GDS file. These files will be generated once your hardening of the user project multiplier is done successfully. Since I already done a successful hardening before, these files are available, but these files won't be available except after you finish hardening your design first. Okay, what other changes we need to make? We need to add the following line to the configurations. Okay, which is setting the global routing adjustment to 0.05. Again, this is an adjustment we needed to make for this project, and it's not something you need to do whenever you start a new project. And whenever you feel that you want to look at any of these configurations, remember that you must go through the README file that was mentioned in the OpenLane configurations. Okay, these are the changes that were needed to be done. Okay, so again, what we did is changing the black box Verilog and views to our project name, and we added the global routing adjustment. We set it to 0.05. What else is there in the user project wrapper configuration file? You will find here, since we are using the first hardening technique, some configuration related to the macro. Okay, so the internal macros, what we do here is that we define the macro power distribution network connections. Here is the macro name, mega project, and we set the PDN connections to VCCD1 and VSSD1. We also mentioned that the macro placement should follow the file called macro.config or CFG. This file is found under the project we are currently working in. If we take a look at this file, macro.cfg, you will find that it has one simple line, basically defining the macro name and its coordinates. Where would it be placed inside the project wrapper, and its orientation? Will it be facing north or south, and so on? So these two things are important, because if you are going to have the user project wrapper containing multiple macros, you must set these configurations well, and make sure that you and make sure that you have all the macros in the macro configuration file, specifying where exactly they should be placed inside the wrapper. What else do we want to talk about in the user project wrapper configurations is that there are some configurations or some changes that are done because there are no standard cells in the wrapper project. What does that mean? So if we go ahead and see this block of configurations, we will find that the following is because there are no standard cells in the example wrapper project. That's because we already hardened our design, and we are using it as a hard macro in our wrapper. So, for example, there is no need for diode insertion or fill insertion or tap decap cells insertion. So, if you are going to use another hardening technique, for example, flattening the design, make sure to remove this part of the configuration files, because this part is based that you are having only one hardened macro in your user project wrapper, and you will not need to use any standard cells while hardening. Okay, so this is a very important note as well. Once we are done with the wrapper configurations, we can go ahead and run the command make. So we can go ahead and save that. I closed the terminal, I guess. Okay. And we go ahead and export the OpenLane route and export the PDK route and run make user project wrapper. Okay, this will go ahead and again start the OpenLane flow to harden the user wrapper. And at the end, you should find, if you follow the steps, you should find the wrapper hardened successfully. So I've already done that step. So again, we are going to quit the flow. And what we need to look at now is the final wrapper GDS file or layout. Okay, so this hardened wrapper is what we've been trying to reach the whole session. The whole session we've been trying to find to reach a hardened user project wrapper that should be ready for submission and fabrication. So this is the final GDS file. Where can I find it? Let's see. Under the user project 132 directory, inside the OpenLane folder, the user project wrapper folder, the runs, you should find your run with the timestamp, but since I've already done it before, so you will go to your run path and then results final GDS, and let's go ahead and open that. And this is the the final GDS of our chip or our wrapper to be exact. As you can find, this green area is the macro, or our SPM, our only macro. And this is the whole project area. What you can see here is that our macro is being placed almost right in the middle of the total area, right? What made the macro be placed in that placement? If you remember, we mentioned the macro.config file. Okay, so the macro configurations right here is the one that mentioned that it should be placed in the following coordinates, right? But do you find this placement of the macro convenient, or the best way you can place this macro? I guess not, and that's because as you can see, all these green lines are the wires connecting the macro to the wishbone pins right here, and the macro is not connected to any IO ports in the top of our area, so it doesn't need to be exactly in the middle. Actually, all its connections in the bottom of the area. So it's better to lower this macro a little bit to have a shorter wire length, and so have less delay, right? So after you harden your macro for the first time, after you harden your wrapper for the first time, try changing the macro.config file to the following parameters. Leave the X coordinate as is, and lower the Y coordinate a little bit. Okay, right? After you are done, go ahead, recheck the file that's been plotted. So if we compare this to that, this one had the macro right in the middle. This one had the macro a little bit lowered, so it can use shorter wires to its connection, and so have a shorter delay. Okay, so this brings us to the final part of the session. And on that note, we want to stress on that electronic design automation helps you in automating mainly the whole process, but still the user, the designer input is important. As you can see, small details like the placement of the macro or changing the configurations before hardening can drastically change the design. So the design automation makes things easier, but you also need to understand what are you doing in order to get the best out of it. And yes, these are the references you could check for the Caravel repo, OpenLane repo, the user project example, and this is a repo on our topic in specific, the SPM. Again, I would like you all to join our Slack channel, Basics to ASICs workshop tutorial under the open source Silicon workspace. Pay our website a visit, as it will have all the sessions and slides as well. Follow us on Twitter and Facebook for news being posted there. And in tomorrow's session, inshallah, we will discuss how to run full chip simulation, and after that run the pre-checks required to be run on the chip before submission, and the steps on how to submit your project on the MPW shuttle. So yes, that's it. Thank you.